There are two different types of fluids, Newtonian and non-Newtonian. Newtonian fluids are what you may be most familiar with, like water, oil, and milk. These are fluids where the viscosity remains constant even when the force applied changes. That means whether you gently tap the fluid or hit it aggressively, the viscosity doesn't change. The only factors affecting their viscosity is temperature and pressure. Keep in mind, high viscosity means the substance will move slower, and low viscosity means the substance will move faster. Newton observed that if a substance is heated, it will become less viscous, and if cooled, more viscous. When attempting to start your car on a freezing cold morning, you may notice that the engine has a difficult time turning over, because the oil in the car is thick and sluggish. Once the engine heats up, the oil becomes less viscous and flows more easily. Newton's law of viscosity is an equation which states that the shear stress or viscous force is directly proportional to the shear deformation of the fluid, the surface area, and the velocity gradient. This equation also includes a coefficient of viscosity value represented by mu and is a constant value dependent upon temperature and pressure. By analyzing this equation, we can see that a Newtonian fluid's viscosity is not affected by the velocity gradient, as its relationship is linear to Newton's law of viscosity. In contrast, non-Newtonian fluids' viscosity changes according to its velocity gradient and experiences a relationship which is not linear to Newton's law of viscosity. The greater the force applied to a non-Newtonian fluid, the least likely it is to change its shape. Non-Newtonian fluids are polymers. A polymer is composed of long chains of repeated units known as monomers that are strung together to yield giant macromolecules. Non-Newtonian fluids are a phenomenon, and understanding the bonds within them has not been easy. A non-Newtonian fluid is an isotactic chain, meaning its chemical composition is linear. The isotactic chain results in a fluid which can be very viscous due to the existence of covalent bonds between adjacent chains, referred to as cross-linking. Highly viscous fluids also have a strong ability to form many hydrogen bonds. In oobleck, the cornstarch molecules tend to be very large since its main component is amylopectin, which is a highly branched enlarged polymer. These large molecules can entangle with other molecules, resulting in a fluid which is highly viscous. When a large force is applied on this polymer chain, the large cornstarch molecules rise up and allow the fluid to act like a solid. However, when a small force is applied on this polymer chain, the water molecules and starch molecules are evenly distributed, allowing for a less viscous liquid. There are two types of non-Newtonian fluids. The first type of fluids are dilatant fluids, which are shear thickening fluids, meaning when force is applied on these fluids, they become thicker. These types of fluids respond in the opposite ways to shear stress. If shear stress is applied, they become more viscous. A mixture of cornstarch and water, which is called oobleck, is an excellent example of a shear thickening fluid. When squeezed, it appears to solidify. Oobleck is a suspension of cornstarch and water. A suspension is a mixture of a solid and a liquid. This mixture is classified as a colloid, a mixture in which the dispersed substance is permanently suspended in a dispersing medium. Here's the chemical structure for a water molecule. And here is the organic structure of cornstarch. For the purposes of making a simple visual, let's represent cornstarch as a large blocky yellow molecule, while water will be represented as small blue circles. Each cornstarch molecule is surrounded by water molecules. When a stress is applied slowly to a shear thickening fluid, the polymer chains have time to move out of the way and rearrange themselves, so the viscosity is not affected. But if a quick stress is applied, the polymer chains do not have time to rearrange. Instead, they become entangled, assuming a solid-like consistency as the viscosity greatly increases. Imagine many cars trying to leave quickly through one exit in a parking lot. If everyone is in a hurry, the cars will become packed together in a tight traffic jam. But if the traffic exit slowly opens up, there will be time for each car to leave in an orderly fashion line. As a non-Newtonian fluid, the ratio of cornstarch molecules to water molecules needs to be within a certain range. If there are too many water molecules, then the suspension will behave as a liquid. If there are too many cornstarch molecules, the suspension will behave as a solid, because there is not enough water molecules in between the cornstarch for them to slide past each other. In this area, there is now a majority of cornstarch, so it behaves as a solid. The second type of non-Newtonian fluids are pseudoplastic fluids, which are shear thinning fluids. This means when force is applied on these fluids, they become thinner. Consider ketchup. You may need to tap the bottom of the bottle or shake it loose to get it to come out. In doing so, you are applying a shear stress to the ketchup, causing it to become less viscous. Other shear thinning fluids are shaving cream, toothpaste, and paint. Non-Newtonian fluids have found their way into the real world and are being utilized in many interesting ways. Understanding the nature of non-Newtonian fluids, scientists and engineers found many ways to use these fluids as a shock absorber and found smart ways to use them for many safety reasons. One example would be speed bumps. New speed bumps in Spain are filled with non-Newtonian fluids in order to encourage drivers to slow down when approaching a speed bump. These bumps are smooth when approached at a slow speed and are hardened when approached at a greater speed. Another example of non-Newtonian fluids are synovial fluids. Synovial fluids can be found surrounding synovial joints such as a kneecap. This thick fluid helps to lubricate synovial joints, allowing them to stay slippery for a natural joint movement. Synovial fluid is a dilatant non-Newtonian fluid, which means it is a shear thickening fluid. This means the fluid can be a shock absorber and is able to protect a synovial joint when a large amount of force is applied on it, such as landing a high jump. And that is all you need to know about Newtonian and non-Newtonian fluids. Thanks for watching. Bye bye now.